Hello, welcome to Breadboarding. My name's Dave Henry, and over the last 13 months I've been building out a PC on solderless breadboards over the last 65 videos or so. And over this time I've made quite a lot of use of devices called Programmable Logic Devices, or PLDs, and a number of people have said over the time it would be good to be able to do a video on how to use these. So this is an example of some of the chips I've been using over the last 13 months or so, and I'll be going into these in a little more detail as we go through a couple of videos to explain how to use PLDs, how they work, and how to make best use of them. So during this series of videos I'm going to be looking at the ATF22V10 and the ATF16V8. So these are two of the PLDs that I've been using on the breadboard PC, but I'm going to be focusing more on the larger one here. As you see, this one has 24 pins. It actually has 12 inputs and 10 outputs. That gives us a total of 22 inputs and outputs and the 10 outputs. So this is what the name means. So we've got 22 inputs and outputs in total, 10 outputs. Now the outputs can also be redefined as inputs, but generally you're going to want to make use of these and outputs. The ATF16V8 is a little more limited in that there are more restrictions on what you can do, and there's various modes that this chip works in, which the restrictions vary by mode. So it's a little bit more complicated to actually get to work. If you're just using very simple circuits like I/O decoders and things like that, then you'll probably be fine with one of these. But as you start to do more complicated things, you're probably better to stick with the 22V10. So this is the first video of the Breadboarding Labs Programmable Logic Devices series. And in this video I'm going to be looking at the background to PLDs, so what the history behind them is, what you can use them for. Basically replace any 74LS logic, pretty much can be replaced with one PLD, can probably do the job of 3 or 4 or more 74LS series chips. How to design them, and I'll be going through a simple example based on one of the samples provided with the WinCUPL programming tool. Look at programming and testing them, and what I wish I'd known 3 years ago. So hopefully you can avoid some of the pain that I've gone through learning to use these chips. So programmable logic devices, as we know now, have gone through various iterations over the last number of decades. So they started off as programmable logic arrays from around 1975. Then these became PALs, programmable array logic, from around 1978, and then probably the big jump in this was around 1985 when Lattice Semiconductor brought out their GAL series, and I'll have a look in a minute about the specifics of that. And the key thing really here is that the GALs here were electrically erasable and reprogrammable. So previously if you made a mistake on these ones and you had to basically throw it away, whereas these chips could be reprogrammed up to about 100 times. One word of warning here, you will need a compatible programmer. I'll be talking about the programmer I use, and there are some open source and do-it-yourself type projects for making a compatible programmer. However, if you actually want to do lots of other chips as well, like EEPROMs and things like that, then you're probably better off to get a medium range programmer. The one I've got cost about £60, for about $80 a couple of years ago. Now there is a good background book on this. It is on the archive.org, however it must be borrowed, so there's only one copy, so whoever gets there first, you'll be able to check it out and borrow it, but please return it, otherwise no one else is going to be able to look at it. That has a good introduction at the beginning, going through all the various sort of history behind these various chips and things, and actually goes through in a lot more of the technical detail about how these things work. I'll include the link here in the description below the video. So probably the most important milestone here is from 1985 when Lattice Semiconductor introduced the GAL22V10 and the GAL16V8. Now these were backwardly compatible with the earlier PAL type devices, but the key thing about these is that the GALs could be reprogrammed up to 100 times, whereas the PALs were single use, so if you made a mistake you had to throw it away. And these replaced many of the earlier PAL devices and really formed a new standard. I don't think it was ever an official standard, but it became kind of like a de facto standard. And many other manufacturers also produced GAL compatible devices, and in fact this is just one of the examples from AMD, just like GAL, only better. So there were lots of devices which are compatible with the Lattice GAL and also all the earlier PAL type devices. So Lattice stopped producing GALs around 2010, 2011, and there were a number of links from the Wikipedia article on the GAL22V10. So this is one of the first ones as reference, and the interesting thing about this is basically they didn't even provide anything sort of backwardly compatible, in that the list of devices they actually provides, these are all sort of dual inline package versions, a lot of these, so PDIPs, and the only option they really provided were flat pack, and they were definitely not pin compatible. So I think Lattice focused on their field programmable gate arrays, so FPGAs, and basically left this market completely. But there are multiple variations of the microchip or Atmel ATF22V and ATF16V, which are pin compatible replacements, and these chips are still available brand new from Mouser and other resellers in DIP form. And the reason why we want this dual inline package form is because it makes it much easier to work with breadboards. I've been trying to avoid using surface mount devices because it requires making sort of lots of PCB adapters. So if we just have a look on Mouser, I'm just going to search for the generic ATF22V, and in fact if we change this and we're just going to go to electronically erasable programmable devices, and if we just look at through-hole devices, apply filters, you'll see that there are still a number of these. If we just filter sort the results ascending, so we can see here that we have a number of chips here, starting with the 16V8, so starting around 96 pence, and there are a number of these with different speed ratings. One thing to advise you about the speed ratings is that generally, yes, you'd want to go for the fairly fast ones, but if you go for too fast it can cause switching spikes and things like that, so you probably don't want to go for the absolute fastest ones, and the faster ones do tend to be more expensive. And you'll see there are certain options such as CZ, I think these are able to do lower power, and also some of these can also do 3 volts. So we've got quite a number of ATF16V8s. You can see here the ATF22V10C, and this is the one probably we're going to be using most of the time, and this is the 10 nanosecond version. You can see they're about £2 a time, and there are faster ones down here, so 7 nanosecond as well. And then these ones down the bottom here, £74, £79, these are military specification chips, so we won't be wanting those. So these chips are still available. The only issue we did have during the COVID semiconductor shortage, then most of these chips were no longer available, and so some of the chips that I've got are actually older ones that I've got from eBay. So if you just take a look at the chips that I showed you a little earlier. So this first one here is a 16V8B, so this is like the ones you can still buy off Mouser. This one here though is a 22V10B, so this one was actually got off eBay, and I think I bought about 10 of them for about £20, although about half of them didn't work. 5 of them did work, so at the time couldn't buy these anywhere else, and so that was okay. So these are more of the legacy type devices. Then this is the one that we'll be dealing with mostly during this video. So this is the ATF22V10C, and the 10PU means it's 10 nanosecond in the plastic package. And there's another one here again. This is a low voltage one, so this is able to go down to about 3 volts, and also low power as well, I believe, this one. So if you're working with modern microcontrollers, so Raspberry Pis and things like that, then I think this one would work at 3.3 voltage ranges, whereas most of these other ones are all 5 volt chips, and therefore we're really working with retro computers like the Intel 8088 and the Z80 6809, those types of chips. So we're going to be focusing on the ATF22V10C. So what can you use them for? Well, the ATF22V10 is GAL22V10 compatible, so it has 12 inputs and 10 outputs, which can also be defined as inputs. Now, one of the biggest challenges I had early on is that the Atmel microchip datasheet does not include all the information you need, and what you really need to do is to look at the original Lattice GAL datasheets to actually find a lot of the important information. And what I've got in the following slides is I've copied some of the key information out of those so that we can review it in a bit of detail. But if you just have a look, this is the GAL22V10 datasheet, and we'll be seeing that there's a number of sections within this document that don't appear in the, so some of these diagrams and things don't appear in the Atmel datasheets, and we'll also be looking at some of these fuse numbers that appear on these diagrams don't appear in any of the Atmel datasheets. You can also see the 16V8. It's interesting to see what the compatible chips, so you can see here are all the PALs that the GAL16V8 is actually backwardly compatible with, so you can see there's a lot of chips that this can replace. So the outputs are able to combine between 8 to 16 terms. So a term really being is an input or a feedback from one of the other pins, and we can combine these with logical AND, NOR, NAND, NOR, exclusive OR and exclusive NOR as well. So the logic rules there are quite flexible. There's also up to 10 D-type latches with a common clock preset and clear. So the common clock preset and clear is a bit of a limitation, and I'll talk about that later on and perhaps in the second video when we try and do slightly more complicated circuits. And that's probably the main limitation I've come across when trying to make use of the PLDs in more complex uses. The outputs are also tri-state configurable at the pin level, so we can assign the output enable term to specific outputs and control those from either one pin or multiple pins or internal logic rules. So you can replace most 74LS logic chips with the 22V10. There are a few exceptions, so chips that have got special outputs like open collector, open drain, Schmitt triggers and flip-flops other than D-type, or if you need actual individual clock preset and clear for each flip-flop, then you can't really use PLDs for that. And if you need 11 or more outputs, then again this particular chip you won't be able to use easily. So typical use in the breadboard PC was things like address and input-output decoders, complex multiplexers in the video output stage. This is where you're actually involving multiple signals to switch between varying numbers of pins, more complicated than the normal 74LS chips would be capable of doing. Clock dividers and including delayed outputs on some of the signals, doing latches, counters and general logic consolidation. So what I've done here is gone through the TI data book that I've got a copy from around 2007, and basically this is just showing probably about the first 100 or so chips which ones are capable of replacing. So you'll see all the ones with the crosses here are things like open collector outputs, Schmitt triggers and things like that. There's about 20 on this page, and you'll see only about half of them are replaceable with PLD, but that's primarily because they have all these sort of buffers and inverters. When we get to the higher ranges, you'll see that the vast majority of all these decoders and things can all be replaced with PLDs, only really these JK flip-flops that we can't do here. And then open collector outputs, 50 ohm line drivers, again we can't do, and this particular one here has 16 outputs, so we don't have enough output pins to be able to do this 4-line to 16-line decoder demultiplexer, but all these other ones we're probably able to do. So I'm just going to take you through the Lattice GAL data sheets and the information that's basically missing from the Atmel ones. So the key thing really here is this logic diagram fuse map. Now fuses in the original PALs were things that would actually be burnt by the programming. With electrically erasable chips, then these can just be reset and reprogrammed. And what you'll see here is we've got the pin numbers on the left hand side here. So the dip ones are the ones outside the brackets. These are the PLCC pin numbers. You can see we've got the output pin numbers here. And this OLMC stands for output logic macro cell. So there's a couple of slides coming up where I've taken the content from the GAL datasheet, which is missing from the Atmel ones. So you can see over here in orange we've got the clock input. So when we've got the registered mode, so these have got the flip-flops, then in fact pin 1 becomes the clock. You can see that Pin 1 comes in and feeds into all of these OLMCs, so the macro cells, as the clock input. You'll also see here that our asynchronous reset is again shared by all the registers. We have one input there, so we can map one logical term to that, but we can't map more than one logical term, so you couldn't have two input pins mapped to that. Then the second half, you'll see, goes all the way down to the bottom here, pin 13, pin 11. And in the OLMCs, you can see that we've got an S0 and S1. Now these are two fuses which determine the function of each of these macro cells. And you can also see down here that we've also got the number of input terms by macro cell. So the ones on the outside have only got 8, 10, 12, and the two in the middle have in fact got up to 16. So you can see the two middle ones have got 16 terms going in. And so if you do run out of terms, it's possible to shuffle the output pins a bit, and you'll probably be able to sort most problems out by moving them around. You can also see down here we've got the synchronous preset to all registers, so this will set all of the registers to 1, but again you've only got one input for that. And down the bottom here I've also got 8 bytes for the signature bytes. So this is also extracts for about the output logic macro cell. I've highlighted the bits probably most important. So the output polarity of each macro cell can be individually programmed to be true or inverting in either combinatorial or registered mode. So the GAL has a product term for asynchronous reset and a product term for synchronous preset that we've just discussed. These are common to all registered macro cells. The asynchronous reset sets all registers to 0 anytime this dedicated product term is asserted. It's asynchronous, so it happens immediately. The synchronous preset sets all registers to a logic 1 on the rising edge of the next clock pulse after this product term is asserted. And then finally down the bottom here we've got a reset operation which sets the register output to a 0, may result in either a high or a low at the output pin depending on the pin polarity chosen. We'll talk a little bit more about the pin polarity as we look at our example PLD. So this is the overview of the macro cell. What we can see here is I've coloured in green the output enable, the orange is the inverted or positive, and the yellow is the registered or combinatorial. It's a bit of a mouthful, that one. So you can see here one of the input terms here goes to the output enable, and again this can be defined whether it's positive for whether or not output enable is determined here, but when we define the pin for this then we can make this active low. Then we can see that the S0 term, when it's 0 then the output here will be inverted. Now you can see here we've actually got an invert here and we've got an invert here, so in actual fact when we've got the inverted output it takes this input and then it will be inverted. If we have the positive then it will take this input and then it will be reversed here. And then you can see that we're either taking the output from the OR array here, so we've got all the various ANDs in the other matrix joining up with these ORs, so this is the combinatorial mode, comes out to here. If we're in registered mode then we take either the Q or the Q bar, again depending on if we've got the positive or inverted. Now there's an important point which is identified in the next slide that says that if we're in combinatorial mode then if we set output enable to be disabled then in fact we can treat this as an input. However, because the feedback for the registered mode comes from here through to here, in the registered mode then you're not able to actually take the input from here when the output is disabled, and there's a section in the next slide that explains what that means. So the modes and the output polarity are set by 2 bits, S0 and S1, which you've just seen, and these are normally just set by the compiler that we use to compile the PLD input file. Output tri-state control is available as an individual product term for each macro cell and can therefore be defined by a logic equation. So this is one of the differences between the 22V10 and the 16V8. 16V8 just has output enable the same for all of the outputs, whereas this is configurable by individual output. And this other bit here says that the registered output cannot be used for dynamic I/O, as can be the combinatorial pin. So that's the issue I was just explaining, because the feedback comes from the Q bar output of the register, not from the input pin. And then on the combinatorial I/O, the output is from the sum term that I showed you, that OR gate with lots of inputs. Output tri-state control is available as an individual product term for each output. If it's on, then it's a dedicated output. If it's off, then it's a dedicated input. So if you ever see the output enable for particular pins to be defined to be 0, then that means that it's a dedicated input and not an output. Or if it's product term driven dynamic, then it means that the feedback into the AND array is from the pin side of the output enable buffer. So that basically means we can take the output pin value and feed it through into the rest of the AND array. So we could actually make a bidirectional buffer, for example. And then this shows the registered mode. So we've got the S0 and S1 is 0 and 0. So that means we have an inverted output and we're using the register configuration. This one we're using register configuration, but we've got the positive throughput there. And then on the combinatorial mode, you can see here with the S0 is 0 and S1 is 1, then the S1 is 1 determines that we've got the feedback coming from the sum output here. And in this case, it's inverted, and in this case, it's a positive logic. So without this information about the macro cells in the Atmel datasheet, then really it doesn't make a lot of sense, and it's difficult to actually work out what's going on. So just take a look at the Atmel datasheet. So we'll look at the ATF22V10C. So this is the one that we'd use by default if we had the option with availability. And I'll just scroll down through this. So it does have a little bit of information. This is the programmable interconnect. This is the fuses and things that define all of the connections between the inputs, the outputs and the feedback. And the logic cell here, it includes a box for it, but doesn't actually tell you what's inside it. Now, if you just have a look at the pins here, so you can see that on the right hand side here we've got 10 outputs, so these are all I/O. Pin 13 here is an input. Quite often this is used as output enable just because the 16V8 has this almost dedicated as output enable. Pin 1, if we're using registered mode, is the clock. In other modes it can actually just be an input. And depending on the way how you configure these, then pin 4 can also be sort of a power disable. So if this is 1, then it will actually put the chip into low power mode. So one thing to be aware of, make sure you're choosing the right configuration, because if you use the version which does this, then your pin 4 may very well turn your chip off when you're not expecting it. Now there's lots of standard sort of voltage stuff, timings and all those sorts of things, but it's really when we get down to some of these things. So there are some things to do with pin keeper circuits, the power down mode. So this is all about pin 4 and the power down mode. So generally with all the 5-volt circuits I'm building, you don't really need to worry about that. Obviously if you're building some sort of low power CMOS type thing, then you might want to worry about this. So this is the compiler mode. So we're going to be using WinCUPL, and in fact we're going to be generally wanting to use GAL mode, so we're going to be using the GAL22V10 configuration. You'll see if you want to use the power down mode, then you'd use this thing with the CP on the end, and if we're using an older style backwardly compatible, then we'd use this P22V10, but we generally just want to use the G22V10 in the configuration. Now this is the logic diagram, very similar to the one that we saw for the Lattice GAL. However, this particular datasheet's got a bit of a problem with it, and it chops it off halfway down the bottom there, so you're missing the bottom couple of cells anyway. And you'll notice that although we've got the numbers along the top there, we've got none of the fuse numbers here, so this doesn't include a lot of the information you need. And you'll see also that there's no mention of the S0 and S1 here, which configure the output, so this is really sort of incomplete. Now in fact if you look at the ATF22V10B, so this is the older chip, the ones I showed you, the diagram in this one actually is complete. So you can see here that it doesn't actually run out at the bottom. So we can see all the way down the bottom. The other one sort of like chopped off about there. So we can actually see this. But again, we haven't got any of the fuse numbers. You could work them out, but it's not very clear. So really, if you're trying to use the Atmel chips, you really need to read it alongside the GAL datasheet. So how do we design PLDs? So I'm going to be doing this using the CUPL compiler for Universal Programmable Logic. Now there is another language you can use, ABLE, and different people will prefer to use different languages. The main reason for using CUPL is just because the free tools available from Atmel for compiling PLDs uses this language. So what we're going to do is define the pin layout in the schematic and the PLD text file. So generally what I try and do in the schematic, I try and lay out the pins and modify the chip that I'm using in the schematic to actually match the layout that I want. And then I also include the sort of pin layout in the top of the PLD text file, and I also will make a chip label for it as well, so that just means less likely to make mistakes, although if you make a mistake in the chip label you can end up with very difficult to track down problems. We assign all the inputs and outputs. So an output can be defined as an input. If the output enable turn is set to 0, then it basically turns the output into an input. So if you ever see output enable set to 0 in a PLD, that will mean that it's going to be used as an input. Now, when you're defining logic rules, there are the basic logical operators, so not, hash for or, ampersand for and, a $sign for exclusive or, and the .d means the input to the D flip-flop. And there's also the .ar and .sp for the reset and preset. Now, one of the key things to note is that the variable names are case sensitive, and if you make a mistake here, what you will find is that you won't get an error, but it won't work. So I'll talk about how you can avoid that problem in a bit. And we're going to use WinCUPL to compile the PLD file into the JDEC programmer file. So the .ged file is the output used by most programmers to program PLDs. So this is a file that I've copied from the gates sample file. So when you install WinCUPL, there is a samples directory, and there are lots of different samples, but they're for a lot of different chips, and some of them are for the more complex flat pack chips, the surface mount chips. There aren't too many for the G22 and the G16, a couple but not many. But this one is actually just a very simple one that actually has two inputs, A and B, and then actually has outputs for the inverse of A, inverse of B, the AND, the NAND, the OR, the NOR. And so we can see down here that the logic rules here are very straightforward. What we've got, I've just put in a diagram here to show the layout of it. So again, this just makes it less likely to make mistakes. So we're only using two inputs, A and B. We've got these outputs. I've defined an output enable just because I thought it was better to explicitly include the output enable. And we can see here that these are all the logic rules. So we've got the inverse of A and B, the AND, the NAND, the OR, the NOR, exclusive OR. What will actually happen is when we look at the documentation file produced for this, it actually converts the exclusive OR into the corresponding ANDs and ORs and NOTs that are required to reproduce that, and also the exclusive NOR as well. And then we've also got the output enables of all of these outputs are now explicitly set by this term here. So this is our very simple PLD. So what do we need to do to program this into the chip? So we first need to install WinCUPL from Microchip. So the link here will take you to the download site. So you can see here, you can just download WinCUPL here. You'll need to expand it and install it. And when you first run it up, you'll need to put in this serial number and type in your company name, organization name, and then you'll end up with something hopefully in the C/WinCUPL folder. So it installs it under the root folder. Now, WinCUPL is not perfect by any means. It's quite old. Most of the references refer to Windows XP, I think, is some of the later references in the README files, and it will crash from time to time. However, What I have found is if you close the project view when compiling, then generally it will prevent it from crashing. What I tend to do is open one of the sample projects. I just happen to use this one, barrel22.pld. If you then open your PLD into that project, it generally won't cause it to crash. Occasionally it will crash after an error, so if you've got a typo or something and it comes up with an error message, sometimes it will crash after that. But generally, if you follow these sort of two things here, you can get WinCUPL to survive long enough to go through multiple iterations of a development cycle. It is possible to run the CUPL executables, which are command line executables, without the Windows wrapper. And there are some sites out there with some scripts specifically to do that, but I haven't found it necessary. So then we're going to use WinCUPL to compile our PLD into our .ged file, which is what we're going to use then to program the chip, which is run device dependent compile. So let's have a look at that. So there's WinCUPL. There are some useful documents. These are in a sort of document folder. The ones I'd recommend you look at are the release notes and the dev help. This includes more detailed information on the individual devices. We'll be looking at that in the next video. I won't go into the details here. So the first thing that I would recommend you do is to open one of the examples. So you can see here, this is from the WinCUPL examples, Atmel, barrel22.pld. Now, it doesn't matter which one you use. But what I've found in using this is that if this project view here is open, then that's what tends to cause it to crash. I haven't gone into the great detail of trying to avoid that. I will perhaps have a look over the next week or so, see if I can find ways of preventing this. But if you turn off that project there, and then we actually open the one that we want to work with. So this is our gates PLD. So I'll just copy the file path to that. Now this will open the project view again, so you just have to close it. And it does a certain amount of syntax highlighting and everything else, but I wouldn't bother trying to edit files in here because sometimes it does crash. So it's easier just to edit in your chosen editor and then compile it in here. So if you go to run device dependent compile, it will say that it's not part of the current project. If we just say yes, and you can see compilation successful. Now if compilation is unsuccessful, you will get some error messages down here. Sometimes it will then crash. There was one problem I had where I ended up actually having to run the compilation from the command line to actually see what the message was, but that's only happened to me once. So it is possible to go to the command line and to do this, but this basically is generally good enough. So this has been compiled. So if we go back to our text editor, and we'll have a look at the output files that we get from here. So just need to make sure I've got the date modified on here. For some reason it's got the creation date. So you can see now that we've got some output files here. So the one that we're actually be using in the programmer is the GED file. And we can see here, it doesn't mean a lot, but all of these things down here are the fuses and whether or not we're leaving the fuse in place or we're clearing the fuse. And there's various checksums and things down here, and we'll go into the detail of what that means in the next video. But the one that's probably the most useful is the doc file. This is just a text file, it's not a Word file. And what this shows is it shows the expanded product terms. So if, for example, we're using the exclusive OR, you'll see that there is no exclusive OR actually in the output here, that it's actually converted the exclusive OR into the corresponding logic symbols that it needs. So A and not B and not A and B. So that is the equivalent of exclusive OR. And you'll also see that the exclusive OR output enable is also set to OE. Now this is the bit that you probably want to be checking on. And the key things here is if you have a label on the left here that doesn't have a pin, then it may very well mean you've made a typo or you've got the case incorrect. And what that can result in is quite difficult to track down problems, in that something won't be working quite right, but it doesn't throw up an error. So always worthwhile checking this to see if there's any gaps here. Sometimes there can be gaps for intermediate terms and things, but if it's one that you're expecting to appear as an output, then you need to check here. And the other thing you'll see here is the product terms used. Now, on one of the examples I'll show you in the next video, I actually managed to get this up to 16. So certainly in trying to do complex rules to a CGA Snow, I actually got up to 16 terms here, and I'll explain how we can avoid problems of that a little bit later. And then it includes, for each of the pins, it'll actually tell us which of the various modes. So the S0 and S1 that we were talking about earlier, that's actually what those two things are there, and we can see where things are being cleared and whatever. So I'll go into how that all works in the next video. So you can see here X, fuse is not blown, dash is where the fuse is blown, and you can see here it's also output us a little chip layout as well. So again, if you've made a mistake in mapping pins, then this will become obvious. So if you want to compare that with your diagram at the top here, then they should be matching. Okay, so we've got our GED file, so now all we need to do is to program it. So I use a compatible EEPROM programmer to program the PLD. So this is a TL8662 Plus from XGECU. So a lot of these were on Amazon for many years. There are a few of them left now, but they've now been replaced by the T48, which I believe is about £59.99 when I last looked on Amazon. Now there are some bundles where they include various adapters for surface mount chips and things like that, PLCCs and stuff like that, so you can pay more than that, but all you need really for doing these ones is the dip, and so this one will work. There are other programmers out there, they're certainly generally more expensive. The only thing I have found is that some of the more exotic chips, so I'll talk about those in the next video, do require higher level programmers, and I've had a few issues with those. So if you're using the TL866 or the T48, then this should be okay for these chips I'm talking about. But just be aware that some of the other ones I'll be mentioning in the next video, so the ATF22V10 and the 750, will require a more expensive programmer. So we're going to start the programmer application. So XG Pro is the application I've been using in all the videos for the last 13 months. And we need to set the chip type to our chosen chip, so the 22V10C. And I always recommend people to read the existing chip first before you program it. If you haven't put it in the right way, it will come up with an error. But if you try and program a chip when it's in incorrectly, you'll probably break the chip. So by reading it first, at least you'll get a warning that you haven't put it in correctly. You can then adjust it, and then hopefully you won't fry the chip. Then we're going to load our compiled GED file from our output here, and then we're going to go through and program and test it. Okay, so I'll just start up XG Pro. So the first thing we need to do is to choose the chip. So if we search for ATF22V10C, Atmel, and you can see here this is actually the first one that comes up. There's all the various variants, so you'll see all the C, Zs and CXs and all these other things, and also the different chip packaging types. But the dip form is what we want. And if we go to the device info, it'll also show you for our programmer where we should plug this in. And you can also see that it's got 5828 bits as well. So this is the fuses, I think, that it's going to be programming. This is the programmer, it's plugged in. I'm just going to take this chip out. I think should be a blank chip. That should be in the right way, yep. So just going to read this first of all, just in case I've put it in incorrectly. So generally you'd expect these to all be ones. So that looks like it's all ones, and we can see 5824. which matches the other information we had. So now what we need to do is to load our GED file. So we've got our gates GED file there, and you can see here a lot of zeros, but there are ones and things around, and then down the bottom. So you can see that it's definitely got some things in there. So if we now hit program, now turn the lock bit off. The reason for doing this is if you have the lock bit, it sort of prevents the reading of the PLD. Now if you were doing a sort of production one, you might want to do that, but for our purposes it's useful to be able to read back the configuration just to check that it's okay. Now hit program, programming fuse bits, then it will verify it, programming successful. And if we read this back again, it should come up with exactly the same thing. So our chip has been programmed. Before I actually take it out circuit and put it somewhere else, I'll put a chip label on it. So this is one of the chip labels I've produced. So you can just see we've got the A and B and all the outputs. I've left the standard terms for the IO 0 and 1 and all the other ones as they are. So before we put this in the circuit, we'll put this chip label on it. Just makes it less likely that it'll make mistakes. Now there's one other thing that we can actually do with this XG Pro. It actually has a test mode here, and you can see that it's got lots of different standard chips there. So there's all the 7.4 series. So if you've got a chip and you want to test it, you can use that. And there is also, I think, one which will try and auto find. So if there's a chip you don't know what it is and you put it in, it will actually try and tell you what it is. But what I have got down here are some user defined ones. And this particular one is one that I defined earlier. And if we just go in and edit this, the UI is a little bit clunky. The main problem with it, it doesn't allow you to define any labels for the pins. So if we click on this first one here, we can see that it's defined as a 24 pin chip. We've got that the ground is on pin 12. We've got the +5 is on pin 24. All of the inputs are just set to 0 by default, and the outputs are set at X. And what X means is don't care, so it won't fail the test, ignore it. And then for these other lines, I've then got varying sort of rules and things, and I'll show you how I've defined those. So if you look at this third one down, we've got a 1 going in on A, and then we've got various lows, highs that we expect here. Now what I tend to do is, because the rules here are a bit awkward, I tend to do a spreadsheet where I just include the tests down here, the pins along here, and then I can actually put my own labels in. So you can see here we've got A and B here. So the default line is just the one I use to copy. Got 0, 0, 1, 0, 0, 1, 1, 1, and then we've got another one where the output enable is set to 1, so that's output disable. You can see here. So generally output enable is enabled apart from that last one. And you can see that we expect this to be high impedance, Z, and all the other ones have got the L's and H's where we expect the different values. So once you program that in, you can then just run test. And if that all passes, then great. Just to show you what happens if it fails. So if we change one of these, for example, and we change the low to a high, modify line, save, and then we test, you'll see that we've got a failure there, and this has come out as high when it should be low. I'll just put it back. And you can actually export and input these configurations, so I'll include the export of this as well in the GitHub. So if you just test that, yes, so that passes. So what this means is we've been able to verify that we've programmed our basic chip. It's got very simple logic rules there, but according to the test that we've defined here, then it appears to work. I'm just going to put the chip label on. We just need to make sure we line this up properly. Okay, so that should allow me to test that okay. Should be possible to read that a bit better. Okay, so that's chip label on. So what I use for doing simple tests like this So I've got this little test rig here, and what I tend to do is I've got a USB cable. So this is just plugged into a cheap USB adapter. For doing simple tests like this, I just tend to put in the power rails there. I just turn that on. So what this switch here does is pulls the outputs there either to ground, or they're pulled to 5 volts using those resistors there, and then that will then allow us to just test this bar display here. So these are all tied to ground here. So if I put an output here from the PLD, then we should actually get values in there. If I just turn the light off, there you go. So that's with them all off, and then you can just about see them coming on. The reason why it's quite dim is because this is probably about a 5k resistor, so these should be a bit brighter if we output it from the PLD. So what this should allow me to do is I'll connect in these 2 lines here to the A and B input, and then we'll plug the inputs to the LED from the outputs of the PLD, and we can see whether or not this works. So I'm just going to plug the outputs. So if we do this like that, we should have inverted down the end here. So invert A, invert B, all the way up to exclusive NOR up the top here. And then I'm just going to put in 2 bits of hookup to go from the 0 here is going to go to A, and then B goes to the second bit here. Okay, so when these are all up, it should be 0. Okay, so we've got VCC, and we just need to do output enable as well. If we don't tie output enable to ground, then we probably won't get anything, so we'll just so got outputs enabled to ground, VCC, A and B are connected to our switch down here. So that should mean if we switch this on now, it should give us outputs. So just turn on the USB power supply. Right, so at the moment we've got 0 and 0, so this is inverted A and B. So if we switch this down to here, yeah, and that one comes down to there, so yeah, they're both off now. So if now we've got 1 and 1 here, then we'd expect to see both the invert A and B should be 0 and should be 1, which is correct. NAND is 0, OR should be 1, NOR should be blank. Then exclusive OR, because we've got 2 the same values, exclusive OR is 0 when both values are the same, and exclusive NOR will be 1. So that looks like that is working, and if we just change one of the other values, we'll see. So it can show that it's working there, and you can see that the brightness here is a lot better. The PLD chips, I think, are able to drive about 16 milliamps, which is quite a bit more than we've got set up over here. This is designed to be a TTL input of about 4.7k pull-up, which is not quite enough to drive the LEDs. So we can see that this PLD is working, and My experience has been certainly with the 16V8s that sometimes it can take a bit of messing around to get them working, particularly when you've got more complicated configurations. So that's how to program and test the PLD. So what I wish I'd known 3 years ago, probably the biggest one which I've shared with you already, is if you look at the Lattice GAL PDF datasheets, then that includes most of the important missing information from the Atmel datasheets. I suspect part of the reason may have been if they were copying it, then they didn't want to reproduce it. It may have been for legal reasons, I suspect. And I've referenced most of that information earlier in this video. I would strongly recommend, if you haven't used PLDs before, use the 22V10 in preference to the 16V8. Unless you had a situation where you couldn't fit the 24 pin into the board rather than the 20 pins, or you were just doing very simple address decoding, I've found the 16V8 modes confusing. Clock is always pin 1, output enables pin 11, but there's all sorts of feedback limits and things, so depending on the configuration you get yourself into trouble with the 16V8. So I would stick with this one unless you really need to do otherwise. Obviously during the COVID semiconductor shortage, then there were lots of these around, but there weren't many of these, so I ended up using more of these than I probably would have normally done just because of the availability. So WinCUPL is buggy, but if you do use the example project and hide the project view before you do any compilation, then it does appear to work. So I was obviously able to use this without it crashing. If I'd had a few bugs and things, then you might have found it would crash. The other key thing really is when you're looking at the logic rules, use the not on the pin definition for active low inputs and outputs. So particularly if you've got chip selects and chip enables, if you define that as active low, so if we look at the chip enable here, so you'll see that our output enable is defined as low, and in the pin definition we've actually put the exclamation mark on the output enable. So what that means is when we're dealing with output enable in the rest of the logic rules here, if output enable is true, then we want to have output enabled. So we don't have to worry about whether or not, oh, output enable is active low. So this makes doing logic rules much simpler. There are one or two occasions where I haven't done this just because I'm replicating logic rules perhaps from the original IBM PC circuit diagrams and things, and it's easier to keep with consistency with the original circuit diagram rather than doing this. But in any other case, I would strongly recommend, if you've got something which is active low, then put the exclamation mark on the pin definition, and then from then on you only have to worry about active is true, active is 1. It certainly makes mistakes less likely. Also check your doc files for typos and terms with no pin assigned and other problems. In the next video I'll probably deliberately put some mistakes in and confuse variable names for case sensitive, and you'll see when you look at the doc file, the pin definitions that I've already shown you will actually show that there's no pin assigned to certain terms, and that will indicate that you've made a mistake somewhere. I strongly recommend reading the WinCUPL release notice and dev help. So those were on the help menu in WinCUPL. Just helps to identify certain things to be aware of. You don't have to fully understand it. I will go through the dev help in the next video and explain what some of the key things in there are. If you're building more complex configurations, you may end up with too many terms error when compiling the PLD. This basically means if the number of input to a certain pin exceeds its maximum number, then if you move the output to one of the center pins, so there are 16 terms in some of the center pins where there are only 8 on the end. So depending on where you put your output, it can have up to twice as many possible inputs in it. And if you still run into problems, then if you've got any spare output pins, what you can do is to combine some of the rules into an unused output pin and then use that output as an input to the rest of the rules, and in that way you can take out half the terms perhaps, so that you can work around the too many terms. Just be aware there's only one async reset and sync preset terms, so if you try and set the reset or preset to be more than one logic rule, then you'll end up with too many terms. So I was trying to do reset based on 2 different sets of rules. Wouldn't let me do it, not unreasonably. If you do have problems with WinCUPL and you get fed up with it, there are some command line batch files. In the next video, I'll look at the GitHub where these files are. I haven't used them myself because I haven't really needed to, but there was one occasion where I did use the command line to work around an issue that I couldn't actually see the message appearing in the output. So good documentation is difficult to come by. The WinCUPL is so old that it actually comes with Windows HLP files. So if we go into WinCUPL, you go into the help here and look at the programmer's reference, you'll just get directed to a very useful Microsoft help page, which is no use whatsoever. So what I have done with these, there are some tools out there you can use to convert these into other formats. So in the next video, I'll show you the contents of those and we'll have a look through some of the documentation which is available to help here. But hopefully there's enough information here to get you up and running. There are a number of samples in the WinCUPL, and if you look at the example list, you'll see they've got the device type. So really we're interested in the G22V10s, and there's a couple of examples in there, but there's not a huge number. So you can see that you can still get useful information from some of the other examples, but certainly some of the sort of higher range ones, the syntax in there is not supported by the chips that we're looking at here. So I'll be going through the contents of these help files, and I will put the files here up on the breadboarding GitHub in the next week or so. So in the next video, what I'm going to be doing is looking at more complex PLD rules, going through some of the WinCUPL samples and documentation. So trying to pull together comprehensive documentation on this is not particularly easy. We'll be talking about the various registers and extensions, so these .d, .oe, .ar and .sp and how these are used. I'll be going through some examples of address decoders, counters, clock dividers and the use of fields, some of the more advanced techniques that you can find from the product documentation. We'll then go in to have a look at the PLDs and how they really work, so how these fuses and terms all work. So we'll be looking at the GED file and explaining what the various bits of the GED file are. If we have time, then we'll look at the ATF22V10 and what the complications and gotchas are there. So it certainly is more challenging to work with these unless you're dealing with very simple sort of logic rules. And then the ATF750C is a 24-pin version of the 22V10, but it has a lot more flexibility. So a lot of the issues to do with, oh, you can only have one clock input, there's only one preset, there's only one clear. This chip has much more flexibility. You can only use this chip with one of the more advanced programmers, which I do happen to have one, but I don't have any of these chips at the moment. I have some of the 2500Cs. I had problems trying to get those to work, and other people on the web have also had problems trying to get those working with the T56 programmer, so I'm still looking into that. So I wouldn't go out and buy any programmers at this point in time until you've seen this video anyway. T48 is probably fine. It's cheap enough that it's going to be useful whatever you use, but the more expensive ones, until I've actually verified that it will work with the 750C, certainly wouldn't recommend anyone to buy the more expensive programmers. So I'm going to end the video there. So thanks for watching. If you don't want to miss out on future videos, then if you can hit subscribe, and if you found the content useful, please hit like. It just helps to make the videos available to more people. Thanks for watching.